Hey there, so this is my project for Math 617, where we're going to work through a section of Needam's visual complex analysis and just kind of elaborate on some of the material that's not covered in our 617 class. So obviously, me being a physics master's student, I have chosen a section dealing with celestial mechanics, so the orbiting bodies around some center of mass. And particularly, we're going to look at like elliptical orbits. So before we do anything, Needam kind of goes through some background about the what's exactly going on for celestial mechanics and what you need to know going in. And that's centrally about central forces. I also have my buddy Einstein here. If you hear any guy like breathing and running around in the background, he's just chilling out here. But with all that being said, we'll get into it. So central forces are a pretty fundamental force in physics. Pretty much any acceleration that is pointing directly towards the origin. And the reason this is fundamental is because it's very easily shown that all central forces are conservative. And that is, they lead to a scalar potential, and that meaning that their curl is zero. So for example, if I take a curl of some central force that's pointing just in the r direction, the best way to prove this is, let's say I have f, and f is equal to some function of r, theta, and phi, and I put it purely in the r direction. It turns out that for central forces, this is purely dependent upon r. So this is r hat. Then what happens if I take a curl? I only need to take the r component of the curl. The curl here winds up being just the theta and phi derivatives of f, of the r component of f. But because the central force purely depends upon the distance from the origin, and it's purely in the direction of the origin, this acceleration, you can immediately conclude this is zero with no further work. So this is why these forces are super important. Because conservative forces lead to a lot of energy-based equations that we like to use in physics. So that's essentially why we like central forces. And particularly, Needam's looking at the solutions to two particular types of motion, which lead to what's known as the ellipsoidal motion. So things that, when you find their solutions, the objects are going to move in some kind of ellipse. So what's well known, and this is the first one, so I'm going to finally start working on the board over here. I hope I'm still in the field of view of the camera. I'm like way over here. Particularly, he's assuming some equation where I'm just going to denote derivatives as double dot or as a single dot. So z double dot being the second time derivative of z. Let's say this is proportional to some kind of z function, and let's just make it equal to z so we can remove some of the constants for now. This very obviously leads to equations of sinh and cosh, exponential function equations. And particularly if this is moving towards the origin negative, this is complex exponentials. So you can immediately conclude that z as a function of time is going to be equal to some kind of parameter. Needam uses the values p e to the it plus q e to the negative it. So these are the values. You can see that if either of these are zero, you're going to wind up just getting like circular motion. So if either p or q are zero, you get a circular motion. And if they're not zero, we've already shown before that this traces a certain size circle and this traces another size circle. So in class, we showed that if you're just taking the average of two circles, you wind up with an ellipse. So this just winds up being an ellipse when you look at the shape of the curve as you parameterize t going 0 to 2 pi. So this is how z is expected to behave. And the other type of ellipsoidal motion, which is much less obvious, is z double dot is equal to negative z to the negative second power. So 1 over z squared. And so this is what's known as an inverse square law. And this is one of the most common types of central forces in physics. So pretty much anything that results from the power dissipating as the distance away tends to show up as an inverse square law, because it's just the same amount of energy being divided by the area of the shell, and that winds up being 4 pi r squared, so it's decreasing as r squared. So this is where most of these come from. So for example, gravity, which is essentially what we're looking at in celestial mechanics, the force due to gravity, this is equal to negative g, the mass of the first object, the mass of the second object, over r squared, and it's in the r direction. So another very quick one, the force due to electrostatic fields, this is going to wind up being Ke Q1, the charge of the first object, Q2, the charge of the second object, over r squared, r hat. And particularly, this is equal to Ke is 1 over epsilon naught 4 pi. So you can see where this 4 pi term, 4 pi over r squared, is coming from. It's basically just measuring the energy dissipation over the shell moving away from an object. So, hey bud, Einstein looks like he wants to help. So moving on from that, essentially this is another very interesting case of a central force where it would be nice to know the solutions. Now I'm going to move outside of Needham's directions for the project here, because he very quickly moves on to this proof. Particularly, he refers to the Kasner-Arnold theorem, and that is basically saying that let's suppose we have some equation such that z double dot is proportional to z to the a derivative. And let's say we have some other equation, the z double dot is proportional to z tilde, so z tilde double dot, z tilde a tilde. So these are a separate equation with a separate solution over here. It turns out that if we allow a plus 3 times a tilde plus 3 equals 4, so if this is true, then we can immediately conclude, taking any solution of z from the first thing goes to z to the m is a solution to z tilde here. And particularly, he says m is equal to a plus 3 all over 2. So this is particularly what we're concerned with here. So let's just check for this equation here. So we have a z to the first, so here a would be equal to 1, and we have another, if you say that's like z tilde, we have a z to the negative second power. So obviously 1 plus 3 times negative 2 plus 3, this is equals, this is 4, and this is 1, so this does in fact equal 4. So now if I take the solutions, if I take z and I raise it to the 1 plus 3 over 2 power, this is equal to z squared. This is going to be the solution to z tilde, okay? So now that I have this set out, I can just simply take my solutions that I've taken over here, and I can square them, and I can wind up getting back to my solutions for z tilde. So I can immediately solve the central force equation for inverse square laws. So I'm just going to do that right now. So z tilde, in this case, is going to be equal to p e to the it plus q e to the negative it squared. And this is going to be p squared e to the 2it plus q squared e to the 2it plus 2pq. Right, so now what you'll notice is this also immediately has an ellipse, but it's less obvious. We have an ellipse with a major or minor axis of p squared, and then the other axis is q squared. It's orbiting a little faster. It's orbiting twice as fast as something you would imagine with the same constants for a linear force equation. And this shift, this winds up being the location of the right foci, okay? So when we take our solutions and we shift everything to the right by the distance, we actually wind up with the origin being located at the left foci. So if our function z looked like this, right, then z tilde, it would look a little more stretched out than this. And particularly, this origin would be the location of the foci, which is actually exactly what we get for celestial mechanics. We get that the foci of the ellipse of an orbit is just the center, or is just where the mass of the system is, particularly where the center of mass of the system is, that the object is orbiting around. So for example, about our sun, we have objects that orbit, particularly Earth is a notable one, and Earth orbits exactly in this motion where we're orbiting around the sun, where we're moving in a very slight ellipse. It's so slight it looks like a circle, but the foci of that ellipse is at the origin of the sun. There are some more extreme objects like comets, if you can Google this, these kind of orbits, but comets orbit around the sun such that they have the foci located directly at where the sun is, because between the two, almost all the mass is located at the sun, so that's where the center of mass lies. That winds up being working through Needham's celestial mechanics. There are a few more details that really only minorly relate to the particular case for this theorem, where we're doing particularly with the case a equals 3, or a equals 1 and a tilde equals -2. But I like working in the general case because it allows us just to see all what's going on behind the scenes, and we don't need to work through the nitty-gritty details of a particular example. But yeah, so this is pretty much how you would, from scratch, find the solution to an inverse square law orbiting body. Particularly note that both of these are negative, so in this case, you kind of need this negative sign to get these kind of ellipsoidal motions. If you don't have this negative sign, you wind up with hyperbolic motion, but it would still be, they would still be similarly related solutions. You would just have sinh and cosh, or e to the t's rather than e to the it, or sine and cosine, depending on how you like to look at the parameterization of these curves. But yeah, that's pretty much all of the celestial mechanics section. I hope you enjoyed.